Welcome to another demonstration of Dmension mathematical universe. Today we will be discussing our new visualization toolkit based on 3D models we have constructed. This demonstration showcases the comprehensive capabilities and advanced computing power of the Dmension, pronounced Dmension, mathematical universal application. This particular demonstration focuses exclusively on Myelin Sheath and Axon structures. Through the system's sophisticated algorithmic framework, we can adjust and integrate precise parameters that generate visually distinct designs for both internal and external anatomical features. This highlights our deep comprehension of neural systems and the significant advantages achieved through proper implementation and guidance. Within the information panel, we feature an image value tracking system that enables users to monitor currently applied parameters while allowing anyone to recreate previously generated designs using our rendering engine. This engine not only visualizes specific coordinates with precision to the 0.00005 decimal place, but also interprets novel geometric forms and incorporates these shapes into its internal database as learning components for future development. Currently, our system employs approximately 197 plus specialized algorithms capable of rendering imagery ranging from fundamental 3D models to microscopic detail levels. While numerous algorithms remain theoretical, we cannot guarantee complete authenticity for all specialized renderings. However, this certainty exists with our Myelin algorithm, which is demonstrated throughout the remaining sections of this comprehensive toolkit. What makes this algorithm particularly compelling is its ability to capture something extraordinary that traditional neuroscience has missed: the dynamic nature of neural boundaries themselves. As we progress through each slide in our demonstration, you will observe something remarkable. The rendered structures refuse to conform to rigid, textbook definitions. In every visualization, dynamics become apparent. The myelin sheaths and axons display fluid characteristics that challenge conventional understanding. These structures are held to no single architectural form, constantly shifting and adapting in ways that static illustrations cannot capture. This observation led to a profound discovery that fundamentally challenges our understanding of neural architecture. The boundaries we have long considered fixed and permanent are, in reality, fluid and dynamic. This represents a paradigm shift from viewing the nervous system as a static machine with rigid components to understanding it as a living river of continuous transformation. Traditional textbook illustrations of neurons with their clean, defined boundaries reveal themselves as mere snapshots of ongoing biological activity. What we perceive as distinct cellular structures are actually temporary expressions of dynamic processes: growth, repair, electrical signaling, and molecular flow, operating within morphological plasticity that allows structures to reshape themselves. Recent research illuminates this structural fluidity. Adaptive myelination demonstrates that active brain circuits gain more myelin, fundamentally altering conductive properties based on use. This occurs throughout adult life, with activity-regulated formation and remodeling changing axonal properties over days to weeks. Axons exist in perpetual metamorphosis, constantly growing, retracting, and sprouting new branches. Adaptive myelination plays critical roles in memory consolidation and motor learning, suggesting our capacity for acquiring skills depends on structural fluidity rather than fixed architecture. Myelin plasticity has emerged as a potential modulator of neuronal networks, indicating that insulation around nerve fibers actively shapes information flow. This represents a fundamental departure from viewing myelin as passive infrastructure to understanding it as an active participant in neural computation. This discovery carries profound implications. If neural structures lack fixed boundaries and exist in flux, then consciousness, memory, and identity emerge from ever-changing connectivity patterns rather than rigid compartments. The self manifests as a dynamic process across flowing networks. This perspective suggests that healing, trauma recovery, and learning depend on fluidity. Rigidity precludes growth and adaptation, while fluid boundaries enable the plasticity and resilience characterizing healthy nervous systems. With no bounds, this discovery has implications that could be life-changing and everlasting. Thanks for your interest and follow us for more.